Hi everyone, this is Niladri, and let me share with you the presentation of networking fundamentals. Now this training session is based on the new CCNA syllabus, which is 200-301, and I will be your trainer for this particular session. Now before we start the training, a little bit of going on the background. Uh, we already have got a ton of information offline, online about networking, about CCNA. I mean, loads and loads of videos are there on YouTube by third-party vendors, by individuals, and so on. So why we need this training? Now, this training was not made to make sure that we create one more training. This was more about to have a more comprehensive, compressed kind of CCNA based training, which is more focused on the labs, live demonstration instead of PowerPoint slides and death by PowerPoint. And apart from that, also to ensure that we are not going for a full-blown CCNA training, which is like 45 to 60 days with all your quizzes, mock exams, lab, practice all, pumped in. It's more like a compressed kind of training, which is easy to go through, and it's got all the live labs, which is showing all the concepts of the CCNA syllabus, and lastly it's enjoyable to go through. So I've ensured that I have given all the concepts in lab formats, and apart from that I have also ensured that I have used minimum PowerPoint slides as possible, and the places where I've used them, they're like kind of must to be used, and have not used PowerPoint just for the heck of using PowerPoint. So that's the gist of the training content. It will be lasting less than 10 hours, of course, with close to 17 labs going through all the core concept of CCNA new syllabus. And also I will be sharing with you the tips and tricks on which you can actually deep dive on each of the concepts and the next steps after the training session. Uh, you can actually go ahead and enroll for a CCNA full blown training after this. So probably like a 30, 45 days or 60 days kind of training. And that training will be more useful and more handy to you because this training will be covering all the concepts which will be absolutely clear to you once you finish the training content. All right, with that in mind, before we start, also one last point that who is this training for? This training is for anyone and everyone who would like to either brush up their knowledge on CCNA or would like to know the CCNA for the first time. You may be coming from a different background. You're not a network engineer. You are coming from a cross-functional team, or you are entitled to give or do some networking job in our CIB, day one or day twos. Any kind of audience who needs some kind of basic granular knowledge about the core concepts of CCNA. Okay, so with that, let's begin our training session. Now, before we start, a few things there. When it comes to learning, each one of us has got a different style of learning. Few of us love to learn by just watching the videos. Few of us take notes. Few of us, purchase books and so on. And we should not be comparing the way we all of us are learning, because that's a unique trait or a unique style that we have got to learn from the content. But when it comes to consuming the content in a very practical and realistic way, I will always suggest that go ahead and get hold of these two books from Cisco Press, which is CCNA 200-301 volume 1 and 2. Trust me, they are beautiful books written in very easy language with all the content of the CCNA and much more than that. So it's good to have those books as the reference point where you can always go back and deep dive on things which you would like to. Now, having said that, you don't really have to jump out of your seat right now and go ahead and purchase those books. You can do it later on. These books are there in Amazon.com sites, and you can definitely go ahead and like place the order. I have seen the volume 2, probably because of the Cisco Press, they just had a lack of the hard copy content or something. They were not producing too much of the volume twos, at least till last month. But now I think it got stabilized. You will find again the volume one and twos in ample numbers there. Now that's one part of the problem, and you can actually also go for the Kindle versions. They are also super to watch and very nicely done. The other thing is that simulators. I strongly believe that just learning through theory will probably not help you out in the CCNA. Then you probably will be a paper type kind of network engineer, but you really have to get your hands dirty. You really have to do the labs yourself, which I'm going to show you, and much more than that. And in order to do that, it's very simple. So probably decades back when I started my journey on networking, that was 2007-8 when I was working at Cisco as a tech engineer. Those days we used to work on the packet tracer, which is the de facto standard for the simulator. But packet tracer, which has evolved from that time to today's, it's a different software. I mean, it supports almost all the commands which you use for the CCNA, which is brilliant. So just using the packet tracer, you will be able to practice, I will say 95% of the concept which are there in CCNA. Probably a few there which you will not be able to do, like art poisoning or man in the middle attacks and so on. Other than that, it's a beautiful tool, and the good point is that, or the best point is that it's free to download. Install it, just a few clicks. You don't have to tweak it. There is no knowledge which you need to really change the content on the back end or doing some server stuff. It's all very easy, UI based, and you can drag and drop the devices and can work on them. The other one is GNS3. GNS3 is also free to use. It's really cool, but one problem with GNS3 is that you have to tweak it a bit. Now, for that you have to learn it a bit. So probably there are some videos, in YouTube and all that, where you can watch them and learn how to tweak the GNS3. But I recommend that that will be more handy in your CCNP days, which probably we will come with a training next year or in next few months. But currently for the CCNA, the packet tracer is more than enough. Even for the CCNP also, I will say more than 60-70% of the commands will be working in the packet tracer. Both are free. Okay. The only disclaimer is that I suggest strongly that do not install these simulators on your office laptop. I strongly recommend you to install them on your personal computers. And if you really want to install them on office laptop, have a word with your manager, check if there is a compliance and so on. Packet tracer, like I said, will not need any extra stuff there, but when it comes to GNS3, you probably will need 6 GB to 8 GB of RAM in your laptop to get it working fine. And also at the end of the entire training session, I will be providing you with some links where you can go ahead and you can do more deeper dive, like what after you have learned the CCNA, then how to prep for the CCNP and so on. All right, so these are the 5 core lessons that we are going to go through, starting right from the fundamentals, and you will be seeing then switching, routing, your security wireless and NAT, and DHCP, IPv6, and IP services. Apart from that, there is a little bit of automation which is sprinkled in the CCNA syllabus, which again I'm going to cover. Now, all these lessons, you will not find too much of PowerPoint slides, apart from a few one, like let's say OSI model and so on. Other than that, the lessons will be full of labs only. So lab 1, lab 2, lab 3, you go and you just check and verify the concepts. Okay, cool. Lesson 1. Now this will be the fundamental, and we always say that if your journey is to aspire to become expert in networking, then you start with your CCNA and then your CCNP, and finally you go for the CCIE, okay, and so on. However, everyone in the industry will say this, that if you really want to move and if you really want to climb up and without a bumpy ride, then make sure that your fundamental knowledge in CCNA is absolutely clear. Okay, and that's why we keep on saying that CCNA as a structure and the fundamentals should be crystal clear. So we are going to start with the fundamentals, of course, the OSI model, without which your training will be incomplete in networking. And then we will go for hub, switch, and router, the difference between the devices, what they're used for, and why are we not using hub these days and we are going for a switch. Ping process, that is one of the fantastic process which will help you to learn the initial way how the packets work along with the different protocols. And we are going to take a deep dive about ping, and I will show you that how ping works, showing in the simulator how the packets are actually going from end to end and how the connectivity is checked. Finally, of course, your subnetting is there, which I'm going to share a content. Also, I'm going to share with you some links and show you some links where you can go and you can practice subnetting and become a master of it. So let's start off with OSI. Now, OSI, as we all know that it's a logical model. It's basically something where you understand the concept of the networking in a layer-wise kind of logical model, right? Open system interconnection, that's what it stands for, and it is there from a very long time. Okay, and the OSI was the first model, and after that we got into TCP IP model. So one of the homework which I will give you is that once you finish with the OSI model and the lesson one, just go back to Google maybe and check out what is the TCP IP model and what is the difference between the OSI model and the TCP IP model. Okay, but OSI model is one of the best models where you can understand the networking in a very comprehensive and nice way, right? And it is kind of, we can say, the process for end-to-end communication between devices in the networking world. Now, OSI has got 7 layers from bottom to top, like you see 7 layers. Uh, the easy way, like what we learned in our time, was remembering a phrase or an adage, and there are many of them. The one which I learned was, please do not throw sausage pizza away. And if you remember the just first alphabets there, is it's like, physical, data link, network, transport, session, presentation, application, right? Now, in this particular model, we are more focused from layer 1 to layer 4. That's where your physical data link, network, and transport lies, and most of the routing and the switching will be done in these layers, and the core concept will be in these layers itself. And the upper layers are 5, 6, and 7, which is like the application layers. Okay, we will not touch them too much, but yes, just know them, they are there. But of course, we will take a very deep dive throughout your CCNA, NP, and IE, from physical to the transport layer. Now, physical layer, the devices that work, like the name says, it's the physical stuff, your cables, even the hub, they are the physical layer devices, or the layer 1. And the way the networking guys, they use the phrase like, this works in L1, L2, L3, and so on. So we will probably use the same kind of, phrasing, like the cables and the hub, they work in L1, right? And these work with the help of signals and bits. Okay, now there is some concept called PDU, or we call it protocol data units. Now PDU is something like a metric with which we measure that particular data frame or the packet and so on. So for physical, the PDU will be signals or bits, zeros and ones, right? Then your data link comes into picture, where we have got the switches. They are in layer 2, and the switches, when you go into there, that's a kind of a core layer, a very important layer on which we have got the MAC address which is working, your protocols, the important ones like ARP, okay, those are going to work there. And once we go like further into the ping process, we will definitely check what ARP is and how it works. The physical layer is in signals and bits, but when you look into the data link layer, that is working on frames. So switches will be working on frames, Ethernet frames, right? Network layer. It's the L3 layer where your routers will work. Again, the OSI model is not a watertight kind of model. Like, things can happen like this, that a device can work in L2 and L3 as well. So these days we have got the switches which work in layer 3 as well, and we call them L3 switch, right? So routers or a L3 switch, and we have got the important stuff here called IP address that works in L3. Important protocols like ICMP that works in layer 3. And in layer 3, your PDU will be packet, right? So layer 2 it is frames, layer 3 it is packet. Transport layer, that's where your TCP and your UDP protocol lies. It's basically the device which will be used in the transport layer, maybe a firewall. Uh, and your TCP is something like your transmission control protocol, which is end-to-end connection, and a three-way handshake happens. It is more, we can say, a reliable connection, and UDP is your user data protocol, which is a non-reliable kind of connection, like your VoIP, your Zoom, your WebEx. These all work on UDP, and the TCP is more like your web services, mail services, remote access, file transfer, and so on, where you definitely need a reliable kind of connectivity. Finally, your top three layers are your session, presentation, and application. And in these, I will just like to say that the application is the topmost, where the end user interaction happens. So maybe if you are sitting in front of a browser or a Twitter and you are logging in there, then that is the L7 layer. All right, and below that lies the presentation layer, where the encryption of the data happens, and below that we have got the session layer, which makes sure that your connection stays there, or the connectivity happens right from your Windows browser to, let's say, the internet or to any server. Okay, now the services which are normally carried by the TCP and the UDP, how do the server at the other end will be knowing that this kind of services has to be carried out? So let's say that you have got a web service, or a mail service, or a file transfer service, or a remote access service. All these will be having a definite port number, and the devices at the other end will understand the services with the help of port numbers. Like TCP has got HTTP, HTTPS, the secured service, SMTP, FTP, Telnet, SSH, all these are there. So port numbers will be, for HTTP will be 80, for HTTPS 443, and so on. Similarly, for UDP, we have got the service like DNS, DHCP, TFTP, SNMP, and so on. So these services which are going to run, they will be running on the backend as the TCP. However, on the upper layer, they will be known by the port numbers, through which the devices will understand that, all right, I'm going to allow this service because this particular port number is open. Okay. Now, a few things here. So OSI model, one more thing which we have to get very clear is about one concept. All the lower layers will be carrying the upper layer information. Important concept. So you have got three kind of headers here. One is the Ethernet header, one is called the IP header, and one is called the TCP header. Now all this will be having the next above layer information with them. Once we get into the lab, especially the ping deep dive, then I will show you that how the Ethernet layer is going to have the information of the IP layer as well. And so on. So, okay, so all the layers, the lower layers will be having the information of the upper layers. The second concept is about encapsulation and decapsulation. So encapsulation will happen from L7 to L1, so where you keep on adding the headers at the source, and it will go from right from your layer 7 to layer 1. And decapsulation is something where you are at the destination, so basically the headers will be removed from L1 to L7 at the destination. Okay, we'll slowly get these points very clearer as we move forward with the training, because like I said, OSI is a conceptual thing, but once we get into the training, you can visualize that, okay, fine, we got this thing done now, and you can just have a mapping done in your mind about, okay, this was there in OSI, and that's how it works. Okay. All right, let's move on. Hub, switch, and router. Now, hub is kind of, we don't use them, these days, right? At least in the corporate world, we do not use hub at all. Probably I have not seen a hub for a very, very long time been used. And we have got the replacement of the hub as a switch, and of course we have got the router, right? So what is a hub? A hub basically is a very basic kind of device which can transmit the data. It's a layer 1 device. It's a non-intelligent device. It is always going to broadcast. So broadcast means when you are in a network, there are three kinds of communication. One is unicast, which is 1:1. One is broadcast, which is 1:all, and one is multicast, which is 1:many. We'll come to that in the subnetting as well. Now, broadcasting means that the hub is the device. If there are 4 ports, they are connected to 4 laptops, okay? And if you are trying to send some information there, all the 4 ports will be sending that info to all the laptops, which we don't want, right? But that's how the hub works. It will keep on broadcasting, and it is also half duplex, which means it can either send only or receive only. It cannot do both the things at the same time. All right, that's a kind of a bummer. And we have got one broadcast domain and one collision domain. The more we get into this concept is CSMA CAD, and I'm not getting into that in detail in theory, but know that broadcast domain is something that hub as a device, as this particular device, will be completely considered as one broadcast domain. Where you send one packet, it will immediately flood that out through all the ports to all the devices connected to it at all the time, right? And the collision domain is only one, which means all the data which is passing through the hub, they will jam each other. So you will always see at once in a while the hub will completely stop like working, the lights will blink, again it will blink for a few times, again it will come back, and so on. So the collision the domain is one, which means that uh, the packets there, or the information which is going to flow through the hub, that will collide, and that will collide within that hub itself, and it will jam up the entire broadcasting or the communication there, which is not at all good, right? Finally, the hub is not going to have any operating system and no memory at all. So it's basically a very, very, very base kind of device which will just allow you to send maybe something to something, and it's like a transmitter, a transmitter receiver kind of device, but it cannot transmit or receive at the same time. Now, switch. People say that switch is the better version of the hub. I will say much more than that. A switch is a much more intelligent device, a robust device, compared to a hub. And switch is basically a layer 2 device, though we have got the layer 3 switches these days. The beauty of the switch is that first time it will broadcast only, and we will see that in the ping lab. First time the switch will broadcast only when you connect the new devices to the switch, let's say your PCs. The switch in itself will be storing something called a MAC table. Okay, and in that MAC table, since the switch works in the layer 2, it will not understand any IP address. It will only understand the MAC address, which works in the layer 2, right? So switches will be storing the address of the devices connected to it. So first time you unbox a switch and you connect the PCs to the switch, it will store in the MAC table about which port, like port number 1, is connected to which MAC address of the PC. Okay, so first time it's a broadcast, because first time it will be chatty, it will be sending out information through all the ports to create the MAC table. Once it receives the information from all the PC that I'm here, and it builds the MAC table. After that, next time onwards, it's a straight unicast, 1:1. It will only send the info from, let's say, port 1 to PC 1, port 2 to PC 2, and so on. Okay, beautiful, right? Full duplex means a switch can send and receive at the same time. It is not like a hub. It will not wait for the transmission to happen and then wait for the receival. It will do all the stuff at the one go. Other cool point of the switch for which I like it is that it's got one broadcast domain. Of course, it's one BD itself. However, each port in a switch is a collision port, or so which means that, let's say a switch is there, And your data will be sent in, and the data, once it goes out, it will flood it. It will broadcast the first time. So broadcast domain is only one, but each port on the switch is a collision port, which means that your switch will not jam inside, which means that when the frames are going through the switch, it will follow the MAC table, and if there is any kind of problem, it will not jam inside, it will not try to reboot like what a hub does. So collision domain is there for each port of the switch. It's of course has got its own operating system, which is the iOS, and the memory. Like I said, MAC table is there, and the lifetime of the MAC table in a switch is for 5 minutes. And this is the way the switches learn. So the first thing is that the switch will be learning the MAC address from the devices. It is called learning stage. The second is the flooding stage, where once they learn the source MAC, they will try to learn the destination MAC by flooding that source MAC through all the devices, and people will respond and reply back. It will have that flooding way to do that. And finally, once it learns the destination MAC address, then it will go for the forwarding state, which means that it will unicast. Like I said, in the MAC table, it will be mentioned which port is for which PC MAC address. It will unicast if your source and destination MAC address is present. So very cool device. It's got almost all the good features which you need to have. Full duplex, of course, one broadcasting domain and multiple collision domains. So each port is a collision port. Let's say there are 24 ports in a switch or 48 ports in a switch. All the ports will be collision ports, right? And finally, you also know that it's going to learn the MAC address, store them. So broadcast is just once, and remaining all the time it's a unicast. Router. So router is the device which works at layer 3, and a router is used to connect to multiple networks. A router is the device which is going to stop broadcasting, which means it will stop that broadcasting at your at one end, and whatever the interfaces are connected to each of the router ports, that will connect to different networks. So multiple broadcast domain, which is amazing, and also multiple collision domain. Again, each port on the router will be having the collision domains there, and multiple broadcast domain as well, which means that a router can connect to multiple different networks based on the interfaces through which it is connected to the networks, right? Full duplex, of course, it can send and receive at the same time. It's got iOS and memory, and it's got a routing table. Like a switch got a MAC table where the lifetime is like 5 minutes, a router has got a routing table where it will store all the next hop, the destination address, and so on, so that a person can just look at, or the router can look at the routing table and find the logic, or know that, okay, how or where the next hop is, and it will act accordingly. Routing table as such has got no lifetime. Okay. And the router also does a very cool stuff called building the routing table automatically, okay, and finding the routing paths with the help of static and dynamic routing. Now, when it comes to static routing, it's pretty much manual. You have to add the routing command with the next hop there, but dynamic routing is amazing, which means these routing actually work on uh, the way that once you install them, or once you configure them, once you turn them on, then they are going to automatically work, and they are going to establish the routing tables and much more. So once we go into the routing lesson, we are going to talk about, let's say, OSPF, okay, which is in the CCNA syllabus. And previously, in the previous CCNA, we used to have RIP version 1 to EIGRP, the routing protocols, which all were dynamic. So dynamic routing is amazing and fantastic because it works on algorithms that will ensure that the devices automatically can build their routing tables and do a lot more than what you can think of. So we'll go and check them out in the routing lessons. So that's kind of the overview of hub, switch, and router. And by now you should be knowing that why do we use a switch and why not a hub? And of course, why do we need a router? Ping process. Now, ping process means the ping is a tool, okay, and that is within your ICMP protocol, which lies in the layer 3. Ping will be checking the connectivity amongst the devices, and we also have got a command called trace that will be checking the best route among the devices. So when we talk about ping, we normally use the ping command to check whether the devices are properly connected or not, or whether there is a packet loss, and so on. Now, there is a very powerful protocol which is called ARP or ARP, and that stands for Address Resolution Protocol. This protocol will actually help or discover the destination MAC address with the help of the destination IP address. We'll check that how and when it does that. So ARP will work along with ICMP to make your ping happen. Now, before we get into the ping process in detail, let's have a look into a few of the things. Number one is about your Ethernet frame. So when we talk about the Ethernet frame or the header, it's got like multiple components, starting with preamble, your destination MAC, source MAC, TN, payload, and CRC, right? CRC stands for cyclic redundancy check. Now, Ethernet header is something which I'm going to show you in the simulation. What are the different components of the header? And we are not going to really deep dive into that header that we'll be doing in the CCNP, but always know that Ethernet frame will not be having a IP content. It's in the layer 2, so it will be having the destination MAC and the source MAC mainly. So the MAC address content will be in the Ethernet header, right? Now in the ICMP we have got two kinds of commands there, or the packets there, or the frames there. So ICMP will be the packet, it lies in layer 3. So ICMP will be having a request and reply, and your ARP which lies in layer 2, that will be having a request or reply as well. Now ICMP, the packet is pretty simple. It's got a source IP, source MAC, destination IP, and destination MAC, followed by PN, type, and code. And your type will change when you're doing the request or the reply. Similarly, your ARP request or reply will be having source IP, source MAC, destination IP, then destination MAC, and followed by the opcode. And your opcode will also change when you're doing the request and reply. So these are the easy ways to know whether it's the request or the reply for ICMP or ARP when you look into the type packet, or the type parameter, or the opcode parameter. Now note that ICMP and ARP, they both are carrying the IP address information. However, your Ethernet frame or the header is not carrying that. We'll check that in detail once we get into the demonstration version or the first lab. Now in the process of ping, your first step will be that your ICMP request will be happening, which is a unicast, and then your ARP request will happen, which is a broadcast. Finally, the remaining ones will all be the unicast, which means that your ARP response followed by your ICMP request once again, and followed by your ICMP reply. They all will be in unicast, apart from the ARP request, which is the broadcast. Now from this flow, things will not be clear, because first of all, I'm not sure ICMP request happened, then why it failed. I mean, why did ARP come into picture? And also I'm not sure that why did the ICMP request happening twice, like first in the beginning, then again at the second last option. That can be only clarified once we get into the next slide, and when I show that to you in the simulator. Okay, so let's go ahead and let's check out how the ping process happens in a basic fashion. So ping process, number one, this is your switch in middle, and we have got the laptop A and the laptop B connected to both sides. Let's say the laptop A has got the MAC address A and the laptop B has got the MAC address B. And like I said, your switches will be having the MAC table, which will be lasting for like 5 minutes. And the PCs will be having the ARP table, okay? Or they will be saving the ARP table, which will be lasting for close to 4 hours, right? So let's say I will be trying to ping from computer A to computer B, and I will type in here as ping 192.168.1.2, which is this guy. Okay, and let's see what happens subsequently. First step is that your ICMP request will be happening. Okay, now request, the frame will look something like this. Number one is your source IP, right? 192.168.1.1. Okay, then your source MAC. So source IP, source MAC, and then you will see the destination IP, which is 1.2, which is this guy, and your destination MAC is not known here because ICMP header, that will be blank because yet this laptop A will not be knowing the destination MAC of the laptop B. I'm just uh, doing it for the first time. Say I've unboxed the switch and I've connected the laptops, right? And of course your 180 here is the type is 8, your PN type and code. Now this particular type will change once we are going for the ICMP reply. We'll check that. Okay, so request, it is 8. So ICMP, it will try to go, but it will fail. It will fail because why? It will not know the destination MAC address, and then it will trigger ARP. Now ARP will be the savior coming. It will do one thing. It will immediately say that, okay, this is my ARP. The first packet, the request packet, and this is my source IP. This is my source MAC. This is the destination IP. And this is the destination MAC, which is the broadcast. You will see all Fs. We have got actually 12 Fs there. The destination MAC will be a broadcast, which means it will flood through all the ports of the switch to all the devices connected. Okay, and this is your opcode, which is 1. Why it is doing that? The ARP first time, like we said, the switch first time will be doing a broadcast because it has to send out that frame to all the devices connected, and then only the device which is having the IP address 1.2 that will respond back saying, hey, this is me and this is my MAC address. So request ARP goes through, and then we find the tables which are getting populated. First thing first, your MAC table got populated. So the port number is 1, and with the 1 your laptop A is mapped. That is the MAC table. And again, once it is flooded, it goes to this guy. It will actually go to all the PCs which are connected to the switch, which you will see in the demonstration in the simulation going forward. But as of now, know that once it reaches this guy will be accepting that because this person knows, or the computer B knows that, okay, it is me because the destination IP is showing up right here, 1.2, which is me. So it will immediately go ahead and it will update its ARP table, which is the source IP address and the source MAC address. So source IP and the source MAC will be saved here. Okay, then the destination, like computer B, will be replying back that it's me with the response ARP, and the reply ARP will be coming up right here, which will be showing that, okay, now the source IP got changed. Source IP is this guy. From here it is going to this side. So source IP, then source MAC, then destination IP, which is 1.1, which is right here, and destination MAC, which is right here, and your opcode will change as well. See, your opcode is 2 here and your opcode was 1 here. So basically your request opcode is 1 and the response opcode is 2. Now once that happens, once the response ARP goes from B to A, then your ARP table, your MAC table on the switch will also get updated because now it will know that, okay, my port 2 is connected to computer B. So update it, done, and then it will also update the ARP table in computer A. So your computer A will be saving like, okay, with the IP address 1.2, which is B, I will be mapping B as the MAC address. Okay, so ARP table and the MAC table, they all are updated here, right? Once that happens, then your ICMP request will start again. And this time the request of ICMP will be carrying source IP, source MAC, then destination IP. Destination MAC will be filled up here, which is B, right? Which is right, this guy. That is filled up, and your also this will be the request packet, so 180, they all are same like the first time. So ICMP goes through, it reaches the computer B, and from B, that is when your connectivity is checked, and it is going to send out the ICMP response. That is when exactly you find that your ping command in the command prompt will start working. So reply will be happening 1.2, that is the source IP right here. The source MAC is B, the destination IP is 1.1, the destination MAC is A, right? And your 1, and this time the type will change to 0, which was 8 in the request, and in the response it's 0, and of course your code is 0 as well. That is exactly how the ping process works. But again, like I said, once you have a thorough look into the lab, which is coming up next, you will get the proper deep dive understanding about the ping packet process. All right, so welcome to the first lab of the series, and we are into ping process deep dive lab. So let me go ahead and pull in some devices here. Let me pull up a switch and pull up a couple of laptops. 4 is fine, and also have the connectivity done. Now this particular software that I'm using is Cisco Packet Tracer, and pretty simple and straightforward to use. Most of the CCNA topology and commands work absolutely fine here with no errors. It's a free tool, but still I recommend strongly to not to install on your office computers. You can definitely do it on your home laptop, which I'm doing right now. Okay, so this is our 4 laptops connected to one switch. Let me go ahead and uh, assign some IPs. 1.1, the MAC address, I will keep it like A's, 4A. This one can be 1.2 and MAC address B. 1.3, MAC address C. And finally 1.4 and D. Okay. Now, once this is done, I will be assigning the IP in a static way to all the laptops. We do not have a DHCP in this topology. 1.1, and let me quickly do it for all the 4 devices. I will just change the last 4 characters of the MAC to make it look clean when we go into the simulation mode. All right, almost done. The last one. All right, we are good to go. Now let me open the simulation mode, and there are a lot of protocols showing up here. I will just pick up the ones which I need. So for ping deep dive, we need to have only the protocols which we need to have: the ARP, of course, and the ICMP. And it's showing there on the bottom, ARP and ICMP. We're good. Now let me go ahead and go to the first 1.1 and try to ping 1.2, 1.1.1.2. Press enter, and let us see what's going on. So the first thing first, you will see that the ICMP was the first packet, the ICMP request that got dropped, and then only we got the ARP request coming up. Now let's check out for the ICMP and see why that got dropped. Okay, let's open it up. In the ICMP, we see that the layer 2 information is blank. Okay, now switch being a L2 device, it will not understand the IP address. It's only got the layer 3 info like the source IP and the destination IP, and the switch cannot really figure out what to do with that, right? if I go into the outbound PDU, which basically means that the information which is traversing out of the device, you will see that here we are seeing the IP header. This is the big IP header, which we are going to discuss once we do routing. And this is ICMP, packet. And we do not have a Ethernet header here. Now that means that the switch really cannot understand what the ICMP packet wants or what to do with that source and the destination IP address. Now, few things here prior to I jump out into ARP request. Number one thing is the encapsulation and the decapsulation concept. Now in OSI model, encapsulation means that at the source, when you are adding headers from layer 7 to layer 1, that is called the encapsulation. And at the destination, when you are removing the headers from layer 1 to layer 7, then that's called decapsulation. And point number 2 is that just remember that all the lower layers will contain the information of the upper layer, which basically means that if it's the Ethernet header, that will contain the information of the IP. If it's the IP header, that will contain the information of the TCP and the UDP, like the port numbers and so on. If it's the TCP and the UDP header, that will contain the information of the services which are going to run between level 5 or the layer 5 to layer 7. Okay. Now, the point here is that when we are looking into this particular headers, we have got three headers here, three key ones. Number one is called the Ethernet header. Number two is called the IP header. And number three is called the TCP or the UDP header. Okay, from the CCNA standpoint, you really don't have to dive deep into the headers, but it's good to have a high level info, which I am going to share with you right away. So let's look into the ARP request. Now, ARP is the protocol that helps you to find out the destination MAC address. So let's see what it does. In the ARP, you will see we definitely have got the layer 2 info, and we are seeing that the ARP has got the packet structure like this. It's called the source MAC, then destination MAC, source IP, then destination IP, and the opcode. So source MAC is A, which is correct. Destination MAC is all F, which is a broadcast, right? Because we do not know the destination MAC yet. So ARP is trying to send it out through the switch to all the end devices connected to the switch. Source IP is the 1.1 and the destination IP is 1.2, which is all correct. Now let's have a look into the outbound PDU for the ARP. And there I'm going to show you some interesting stuff. So first of all, you look into the Ethernet header or the frame here that is showing up here, and below is the ARP, right? Now in the ARP, if you look, you have got the target MAC as 000. However, if you look at the top in the Ethernet frame, you will see the destination address or the destination MAC is all F. Now, did not we say that ARP is going to send out all the broadcast in Fs? Then why the ARP is showing here all zeros and the Ethernet frame is showing all Fs? The reason is that Ethernet frame is a pure L2 frame, which means that there is no IP in information here at all. We all have got the source IP, which is all A's, and the destination, the source MAC, which is all A, and the destination MAC, which is all F's. That basically means that the Ethernet frame is actually doing the broadcasting. But in the Ethernet frame, we have got something called a type. Now this type is X0806. If it's X0806, that means it's ARP packet information. If it is X0800, that means it is about a IP version 4. Okay. Now X0806 means this entire frame is carrying an ARP with it. However, since the Ethernet frame is not having any IP info and it's a pure layer 2 protocol, the switch will look into it and say, okay, fine, the destination MAC address is all Fs. Let's do that. Let's send out all Fs to all the end user devices. There is one more point here, that is Ethernet frame is a layer 2 protocol, and ARP technically is a layer 2.5 protocol. So Ethernet frame lies on the bottom, and that will carry the upper layer information because ARP is 2.5, and that's why the ARP thing is showing up here, X0806. But if you go down to ARP, it says that it's all zeros in the target MAC. Now the reason ARP is in 2.5 layer is because ARP lies in the boundary between your L3 and L2, and that's why ARP has got both the MAC information and the IP information as well. Now looking at the ARP, we have got few things here. We have got the source MAC, which is A, all correct. The destination MAC, which is all 0, which is flagged by the Ethernet frame as all Fs. Source IP, of course, 1.1, and the target IP is 1.2, and the opcode. Opcode is 0x0001. Now when it is 0x then 0001, that means the ARP is a request ARP. Okay, the response ARP will be in the form of 0x002. Now why we need that? Because when the ARP packet will be broadcasted to all the devices, the device which is the correct one will pick it up and will know that there's a request for me, and it will send out the response ARP packet in the form of opcode 0x0002. Okay, so now let's see what happens in the next step. ARP request going to the switch, and now from the switch the request ARP will be broadcasted to laptop 1, 2, and 3. Here you go, all the 3. And you will see out of all the 3, the laptop 2 and the laptop 3 is going to discard the ARP. Why? Because when they open the packet, they see it's not meant for them. It is meant for 1.2, and they are 1.3 and 1.4. Okay, but 1.2 will accept the packet and say, it's for me, I'm 1.2, and it will immediately see, it's a opcode is 0001, which means a request. Now I have to send out a response to this guy saying that I'm 1.2 and my MAC address is BBBB, right? So this will again trigger the response ARP back, and while it does that, it will also update its own ARP table, which will be showing that the MAC address A belongs to 1.1, and once it will reach the switch will update its own MAC table, which shows the port number that goes to the laptop 1, right? Now response packet of ARP, let's check how it looks like. Okay, we are here, and here you will see that in the response we have got the source MAC as all Bs, which is great, and the destination MAC as all As. The source IP is 1.2 and the destination IP is 1.1, which is going back to laptop 0. Inbound means the information which is coming inside, and outbound means the information which is going outside, right? So this one, if you look into the inbound outbound, you will see that the opcode has changed now. It is 0x0002, which means it is a response ARP going back, and this response ARP has got the MAC address captured of the destination IP, right? Ethernet frame, now it is all clear. Your source MAC is all B, and your destination MAC is all A's. You are still in the 0806 because you're containing the ARP within you. And for the ARP, you have got the source IP, which is 1.2, the destination IP 1.1. Of course, your target MAC is the A, and your source MAC is B. Now this B is captured into the ARP response packet. All right, all good. Now let's see the next step. This packet will be getting back to laptop 0. Once it goes back, immediately what will trigger is ICMP request, because ICMP request was discarded in the beginning, because it was not having the layer 2 information, or basically the destination MAC address. Now let's see what's going on there. If I go to ICMP request, yeah, now let's see. It says clearly that the ICMP is having the A to B. The source MAC address is A and the destination MAC address is B. And if you go to the outbound, it is having the Ethernet frame here. Now what has changed here? Of course, the source MAC address is A and the destination is B, but you will see the type also changed in the Ethernet frame. That is now X0800, not 61, which was the ARP one, right? 800 is basically meant for IPv4, because now this is containing the IPv4, I mean the IPv4 packet. So the type has changed. Now this has got two headers. Of course, number one is the IP header, which has got the source IP and the destination IP. They both are showing up here nicely. And if I go down, you will see the ICMP packet, which basically is the type. If you remember, the ICMP request type will be 8 and the response type will be 0. So all is showing absolutely correct here, and this is the ICMP request. Now let's see what happens with this. Um, Remember that in the entire flow, only the request ARP is broadcast, but all the other flows like your ICMP request, ARP in response or ICMP response, they all are unicast. So let's go forward. Now the switch will directly push the ICMP in request to the 1.2, which is happening now. And now this guy will be sending back the ICMP response. Let's go for the response. Yes, that's the response now. Let's have a check how it looks like. That's the response. And you will see it is going from source MAC address B to the destination MAC address A. Inbound, if I check, this is your 0800, which is IP version 4. Your destination is A and the source is B, which is all correct. That is your IP. And if you go to ICMP, the type has changed to 0. The type was 8, right? The type has changed to 0 because this is the ICMP reply. Okay. And this ICMP will be getting back to the laptop 0 or 1.1, and that's when the ping happens. So now let's check the ping window again, and you will see the response has come back. Reply from ICMP response packet 1.1.1.2. I mean, the ICMP packet size in Windows is 32 bytes. Okay, from 1.2, the packet size is 32 bytes. In Windows, it is 32, and when you are going to do it from a router, then it will be 100. Okay. Now, what is this TTL 128? Now, TTL 128 will remain the same when you are trying to reach a device within the same network, which means you have got, say, one switch and 20 devices connected. Then each of them, if you ping, it will always be showing 128. However, if you connect a router and if you want to reach to a separate network, okay, the number of hops you take or the number of routers you add, that is the number, the TTL number or the time to leave will decrement. So looking at the TTL number, you can always say that how many routers or how many hops you are away from your destination network. It's an easy way to find out. Let's say you have got one hop to go, then the TTL will be coming down to 127. Okay, so let me show it to you right now, and let's open up my command prompt and let's ping something. Ping www. Let's say google.com and enter, and you will see the TTL is coming down to 117, which basically means that you are 11 hops away from Google server. So 11 hops away means that 11 routers you have to pass through to reach the Google server. So that is 128. Okay. Again, the 128 value is for the Windows. If you're trying in Linux, it will be like 64 as default. If you're trying from the router, the default will be 255. Okay. So that's all from my end. I hope you enjoyed the lab on the ping deep dive. Thanks a lot for watching. Subnetting. Subnetting is considered one of the core skills of a network engineer. Having said that, if you go to a CCNA exam, you probably will not be asked a single question on how to do a manual subnet. And if you're working in a corporate or enterprise, probably most of the time you will be using a specific subnet calculator to calculate the range of the subnets along with the number of hosts with few simple clicks. Still, subnetting is one of the basic skills and core skills of a network engineer. Why? Because it's the kind of the knowledge via which if you can look into an IP address range, then you can break it down into multiple subnets, into viable and practical groups without wasting IP address. It's a simple concept. However, it takes time to become an expert on that. So in this lesson, we are going through all the concepts of the subnetting. At the end of the lesson, I will share with you how to use the subnet in a practical way and how do we create subnets and how do we save the IP address spaces. Uh, Finally, I will also share with you a few websites where you can go ahead and you can practice subnetting and become a master of it. All right. So let's dive in. Let's start with IP address. Now, when we say IP address will be into two groups. One is the IPv4 or version 4, and one is the IPv6 or the version 6. Now, version 4 of IP address, the most widely used and the most popular, and our entire subnetting course will be based on IP version 4, is basically a 32-bit address, on which we have got 4 octets and each octet is 8 bits. So if you look at the bottom, let's say that these are the 4 squares or the 4 octets. Each of them has got 8 bits into that, which if you calculate like 8 multiplied by 4, it comes down to 32-bit address. IP version 4 is always in a dotted decimal format, which means we use only the decimal numbers with 4 octets and with dots in between. A typical example of an IP version 4 or an IP address will be 192.168.1.1, right? Now, if you want to know what is the maximum number of IP address that can be allocated within IP version 4, the answer is 2 to the power 32, and that will come down to closely 4 point change billion IP address, which sounds like a very big number. But since IPv4 has been used for quite a few decades in the past with huge number of corporations and enterprise and companies, IP version 4, especially the public ones, which I'm going to talk about later, they are getting crunched. They are getting depleted. We do not have much of them for practical use. And that is why the new concept, I will not say a brand new concept, it's been there for some time now, that is IP version 6, and which has got a huge amount of bank or pool of IP address, which will last for decades after decades. Okay, and why it is? Because IP version 6, the maximum number of IP address that we can accommodate is 2 to the power 128. That's a huge number, right? Now, IP version 6, number one, in the CCNA syllabus, we have got a crux of it, which I'm going to share in a later part of the lesson on only IP version 6. This is just a kind of a touch base. Um, in the exam, you will not be asked to do a subnetting on IP version 6, or you will not be asked to do a lab or a practical networking on IP version 6. It will all be based on IP version 4, but it's good to know about the basic concepts about IP version 6. IP version 6 is a 8 hexabit and each hexabit is 16 bits. Now, if you look into the left hand side, it's just a double. This is like 4 octets. This is 8 hexabit. This is 8 bits. This is 16 bits. Now, if you look at the bottom, you will see that this is like 8 boxes and each of them is having 16 bits inside. And if I calculate the total range there, it is 16 multiplied by 8, which brings to the number 128. Okay, and it's a hexadecimal with colon. So if you look into IP version 6, it's a combination of decimal numbers and hexadecimal numbers. Basically, it's 0 to 9, which will give you like 10 in the range, and A to F, which gives you 6 in the range. So 0 to 9 and A to F are used, which gives you complete 16 bits. And if you look into a typical IP version 6, it's a combination of decimals and alphabet with no dots, but with a colon in between. That colon is kind of the divider between the multiple hexabits. Okay, so let's park the IP version 6 right now, because your entire subnetting will be based on IP version 4. And once we get into the further lessons, then one of them I will be surely explaining the IP version 6, which is in scope of the CCNA syllabus 200/301. So let me quickly go ahead and let's move on to the next concept. That's about IP address. So IP address in version 4, we already know that 32-bit address divided into 4 octets with dotted decimal notation, right? Now IP version 4, let me quickly pull out a marker here. So if this is your IP address, which is 192.224.220.248, then you will see this particular address will be broken down, okay, into 4 octets, and these octets will be in decimal notations, or rather these octets in the computer will be in the binary notation. Okay, so in the computer, if you type the binary here, sorry, the decimal here, then computer will not understand 2, 3, 4 and all that. A computer will only understand 1 and 0, right? And so the computer will convert your decimal IP address to a binary format, and this will be stored in 4 octets. Okay, now let's zoom in to one of the octets and see what are the values in the octet. So if I go there, let's zoom into one octet and see the fixed values. If I want to know the fixed values of each of the bit sector in the octet, then they will be represented by the multiplication table of 2. That the chart of 2, like 2 to the power 0 will be the bit 1, 2 to the power 1 is the bit 2, 2, 3, 4, 5, 6, 7 will be going straight to your last 8th bit. So if you just take the numbers here, 2 to the power 0 is 1, then 2 to the power 1 is 2, then 4, 8, 16, 32, 64, and 128. All these numbers are the fixed numbers in a 8-bit octet. And if you just summarize the numbers, if you add them up, like 128 plus 64 plus 32 plus 16 plus 8421, you will be getting the number 255. And that is why we say that octet maximum value is 0 and minimum value is, I'm sorry, the maximum value is 255 and the minimum value is 0. Now why we say that? Because if you look into the binary format, if I turn on, I mean, I can either turn on this to 1 or 0, right? Now, if I turn on all the boxes here to 1, it will add up to 255, because here the 1 means 128. The second one box, the 1 means 64, like that. If I make all of them 1, the number will be 255. If I make them all 0, the number will be 0. And that is the reason we say that minimum octet range is 0 and maximum octet range is 255. Okay, now the other thing which I want to show you here is that how to convert a decimal to a binary. Now you do not have to do that. Being a network engineer, you may not do that at all. But like I said, it's always good to know the basics well, so that you understand what exactly is happening on the background. So let me quickly show you how do we convert decimal to binary. And let's go back to our school days. I'm sure that all of us has gone through this drill in the school days, and we used to call it Boolean algebra. And there we used to do the conversion of the decimal to binary and binary to decimal as well. Very simple. We'll just brush up our knowledge there. So if I pick up the last octet, 248, now we will see how do we convert this particular decimal to a binary format. So the rule is that you keep on dividing the number by 2 till you hit 0. So let's say that 248 by 2 will be 124, right? And we have to write down the remainder. The remainder will be 0 here. It's a straight divide, right? Now I will divide 124 by 2, which is 62, and I will say remainder is 0, right? Now I will divide 62 by 2, 31, and I will say remainder is not 0 here, it is 1, sorry, it's 0, right? So Till now it is 0. Now I will divide 31 by 2, which is 2 into 15, we get 30, and 31 minus 30 is 1. The remainder is 1 here. Then I will say 2 into 2 multiplied by 7 is 14, 15 minus 14, remainder 1. I will say 2 into 3 is 6, 7 minus 6 is 1. I'll say 2 into 1 is 2, 3 minus 2 is 1. And finally, I will say 2 into 0 is 0, and 1 minus 0 is 1. That's where we stop, because like I said, we will keep on dividing by 2 till we hit 0. Now, if you look at the remainders on the right hand side, all the zeros and ones, we are going to take a bottom up approach. Like we will take that sequence from bottom to top, which is 1 1 1 1 1, like 5 ones and 3 zeros. And if you look into the last octet, it is exactly 5 ones and 3 zeros. That is how we calculate or we convert a decimal to binary in the computer. Like I said, you may not be doing it at all, but it's always good to know this, because this concept is pretty easy and simple. Now, the other thing which I would like to show you here is that how to convert a binary back to decimal. Now, let's say that looking at this octet, let me pull out a marker here, one sec. Looking at this octet, let's say, okay, or let's say the first one, because we have done with the fourth one. The first one is that we are saying our first 2 bits are on and the remaining are 0. Now, how do I find the decimal value from this? I just have to check what is the value which is assigned to the first bit, second bit, and so on. So first bit is how much? 1, which is 128. The second bit is how much? 1, which is 64. And 128 plus 64 will be 192. And remaining will stop with 0. We don't need that. Why? Because we are saying the IP address is 192. So like that, once we reach that particular value, we are going to make the other octets or the other bits as 0. Okay, very simple. Now, let me show you one more thing. There are a few websites where you can actually do this pretty fast and easy. Let me just show you one of the sites. Probably IP to binary. Okay, there are plenty of sites. Okay, so browser link is just one of the popular ones. You can just type in something like 192.168.224.248 probably, and it will say convert to binary, and immediately get the conversion done. Okay, but like I said, it's always good to know how the basics work. So having said that, let's come back to our discussion. So that's about the IP address. Now you know that how the 4 octets are and how do they look like, how do we convert them, and most important of them all is that we definitely have to know what is the value of each each bit in the octet. Okay, the multiplication table of 2. So let's move forward. The second one is about, or the concept that we are going to talk about is public IP and the private IP. Public IP is what? The IP address which you can use in the WAN. Basically, your local network, okay, at your company will be the LAN, right? And once you move out of LAN and you move out to the internet or external world, then you are going to be calling it WAN, right? Wide area network. And there we are going to use the public IP, because private IP address or the IP address which we are showing like below, starting with 10 and 172.16, 192.168, those IP address they cannot traverse in the WAN. All right. So public IPs, you basically have to purchase it from a ISP. Your internet service provider will be selling you a public IP address. And remember one thing, with this comes the concept of IPv4 and 6, because V4, we are slowly into the shortage or extinction of public IP address. We don't have much more them to be used in the future. That's why we have got the concept coming up called IPv6. Now looking into this public IP, let's go through them one by one. So we have got few classes there. And looking at the classes, I will say that we have got 5 classes, class A, B, C, D, and E. And each of these classes, they come with a particular range of the IP address. Just looking at the first octet, you will be able to say whether it falls under class A, class B, class C, class D, or class C. So class A is starting from 0 till 126, right? B is starting from 128 and going till 191. Wait, we do not see the 127, right? We saw that 0 till 126. Then where is this 127 gone? We are starting from 128 from 191. Now that 127 is actually called as your loopback address. Now we have got a concept in the routers called loopback interface or loopback, routing. That is a different concept. This is something else. These two like loopbacks are not the same. Loopback in 127 means that this is the particular address through which you are going to check the connectivity of your LAN card or your NIC card. Okay, so what happens is that normally in the desktop, troubleshooting, that's one of the troubleshooting steps. A customer calls you and says, I cannot connect to net, and you will be checking like one by one things. Let's say the physical connectivity, wired or wireless, how the home router is working, so on. And finally we'll be coming to a point where you will say, okay, let's ping 127.001, and you will check if the ping works. If the ping fails, there is some problem with the network LAN card, right? So on this one, I will just want to show you a few things here, and then probably we can go from there. Let me open the command prompt, and before the command prompt, let me just show you ncpa.cpl. ncpa.cpl is the command which you can type in, and you can directly enter your network card interface. So let's see what's coming up there. I don't think it's still there. Let me just take this annotation off. Probably have to go to desktop mode. Yes, we are seeing the ncpa.cpl. Now that is my network. I'll just go ahead and right click on this. And once I right click, I will go to properties, and you will see that I have got the TCP IP. I will click on this and I will go to properties here. Now, if I go to the IP address, I have got an option there to manually type in an IP address, right? Can I use one there? Let's say if I use one and I press enter here, like subnet mask, accepted, right? What about if I use two? Accepted? Yes, done. What about if I use 126? Is it taken? Let's see. Taken, right? So they are all being taken. What about 127? The moment I type, it tells me it cannot be taken. It tells me clearly IP address starting with 127 are not valid because they are reserved for loopback address. Please specify some other valid value between 1 and 223. Okay, so that is the thing. You cannot use your 127 for IP routing. It is a loopback address through which you can check the connectivity with your LAN card. So now we can go to command prompt, and I will be showing you this. Let's say ping, and I do 127.00.1 and enter, and you will see the reply is happening, which means my LAN card is working fine. Okay. Now here a few more concepts has to be made clear. So let me quickly open up a window here. Now when I say 127, let's say dot 0.0 dot 0, right? That is that's the address we have got. And let's say I'm trying to just break it further. So I will see the ranges. So I will say 127.0.0.1. That can be one IP, right? Then I will say 127.0.0.2, and I will keep on going. I will say 127.0.0.255, right? Similarly, I will say 127.0. Then I will say 1.0, and I will keep on going 127.0. 2, 3, 4, 5, and come to 255.0, and we can change this as well to 255. So like that, we will come to a point where we will say that 127.255 dot 255.255.255 is the last IP address. Now, the first one which you see there, um, this particular IP address is called the network ID, 127.0.0.0. The first one in your range is the network ID. And the last one in your range, the 127.255.255.255, that is the broadcast ID. You will not be able to use these two IP address for your IP address nomenclature. Okay, because the first one is your network ID and the last one is your broadcast ID. So what you can use is that between the network ID and the broadcast ID, what you have got from 001 till 255, just before that, whatever you get, that is your entire valid IP address range. That's the only one which you can use. And that's why you will normally see that when you are trying to use a default gateway, right, which we are going to talk in the routing, you will see that it is always like 192.168.1.254. We are not going to use 255, the last one is for broadcast. We're going to use one which is just ahead of the broadcast, which is 1.254. Okay, so that's kind of the concept about the 1 to 7. Let me remove these drawings and let's go back to the slide. Few more things I would like to talk about here. One is that your 0000, okay, that particular address is normally used for default routing. We will not use that in a normal IP address nomenclature. I will talk about that in the default routing or in the routing concepts. 1 to 7, we have seen that. What is the feature there? Now let's go back to the table. So we were in the A class, which is the range we know. The B class is 128 to 191. C class is starting from 192 to 223. Okay, and if you remember the window that popped up while I was trying to type the IP address, like 127, it told that type in something valuable or something valid between 1 and 223, right? The 223 is the last one which you can use for the class C, because D and E will not be used for WAN and LAN. Class D is a very unique one, and that is used for multicasting. So multicasting is what? In internet or in network, you have got three types of communication which goes on. One is called the unicast, which is 1:1. One is called broadcast, which is 1:all, and one is called multicast, which is 1:many. Okay, now 1:many, but not 1:all. That's a trick there. So 1:many means that probably it's a kind of a channel where you tune in. You have got a video channel in your company where probably your leaders speak in a video cast or a podcast, and you are subscribed to that channel. So after subscription only you can watch that channel. People who are not, they will not be able to watch that. Like a television, you tune into a channel and then only you can watch that. All the channel content is not broadcasted to all the channel frequencies at one shot, right? That's called multicasting. And class E is from 240 to 254, and that is actually used by research and development, defense, for federal purpose, for government purpose. Okay, that's not used for normal LAN or WAN. So remember one thing: your public IP, you get it from your ISP normally, and it's chargeable. And A to B, all these three classes will generally be using the public IP, majorly for the WAN. And it can be used for the LAN as well, though people do not use a public IP for a LAN. That will be very costly to use. Now, coming down to your private IP. Before I jump into the private IP, just two more points here. Let's say class B. Class B also, there is one range which we cannot use for IP nomenclature, that is 169.254.00 to 169.254.255.255. And why is that? That particular address range is called APIPA, or automatic private IP. Now, APIPA is a concept in DHCP. And once we get into the DHCP full-blown lesson, I will show it to you what is API-PA, and that is something which we cannot use in a normal IP address nomenclature. Now the last one is 255.255.255.255. That is the global broadcast address, and that particular address we will not be able to use in a normal IP address nomenclature. Cool. Now let's come down to private IP address. And remember, private IP address will only be used for the LAN, the local area network. These cannot be used or routed over the WAN. Okay. Now your private IP address are ABC we have taken for the classes. So A is from 10 till 10.255.255.255. For class B, it is 172.16 till 172.31. And the class C is 192.168 till 192.168.255.255. So basically, three ranges they are shown, which all are used only for private IP. Now, let me just show you something here, and probably you will get the concept much clearer. So let me remove annotations and pick up something else. Let's say I pick up a IP, right? So let's say it is 192.192.192.192. Now, this address is a public or a private? It's definitely a public IP. Why? Because see, you always have to look at the octets which are locked down for the private. The lockdown octet for the private is 192.168. Those two has to match, and then only you can look for the third and the fourth, right? But here it is not matching with the first two octet. The first one though matches 192, but after that it is 168 here, and we are again saying it's 192 there. So it's a public IP. What about 10.10.10.10? Is that a public IP or is that a private IP? So again, that will be completely a private IP. Why? Because your first octet is locked in the class A, which is 10. If something starts with 10, automatically that has to be a private IP. So these are the ways you will be knowing what is a private IP and what is a public IP. Generally, in the corporates, we use the 10 IP address a lot for private IP, and also we use a lot of 192.168. So those two are used mainly for your private IP nomenclature. Cool. So let's move on from here and go for the further concepts. Okay. Now this one is kind of your gist of the subnetting, and this slide is very important. Okay, so let me just pull up annotation here, and then we can go from here. All right. So first thing first, we all know this multiplication in a table of two and how each octet looks like in terms of each bit, value. Like it goes from 2 to the power 0, 1, 2, 3, 4 till 2 to the power 7, and the numbers like 1, 2, 4, 8, 16, 32, 64, 128. Correct? Now, again, we come back to class ABC. Now, class A. So the first thing first is that every IP address will be or can be broken down into a network part and a host part. Your network is the network address, and the host is the number of the users who can get connected to that particular or within those particular IP address range. Okay. So class A, the first octet is used for network, and the remaining three octets are all host. Okay, so if the first octet is used for network, then we can actually write this address something like this. We know that the first one is like kind of locked on, and the remaining are like 0. So we can say that we can write 255.000. That is your subnet mask. Why we can write that? Because we are saying, since the first one is the network, it is locked, so all is like 1. All the bits can be put to 1, which is the maximum value will be 255, and the remaining ones will not matter, so all 000. So 255.000 will be the subnet mask for the class A. Similarly, class B, the first two are kind of locked, which is network, which is 16 here, and the remaining will be host, which is 16. They're blank. So if these two are locked, then the subnet mask can be 255.255.0.0, right? Similarly, for the class C, we can say that the first three octets are blocked or locked for the network. So we will say 255.255.255, and the last one, the host one, we will say as 0, because that is a subnet mask, so 255.255.255.0. Okay, just do not take into account of this 255 on the bottom, because that is something I wanted to explain, that what is the maximum value of all the octets. Okay, however, when it's a subnet mask, it will be 255.255.255.0 for class C, because first three is locked in for network, so all 255, and the last one we have kept for playing, that is 0, that is for the host. Like that we remember. Okay, now there is a better way of writing the subnet mask. We say that 255.000 is the subnet mask for class A. Can I write that as something /8? Okay, we can also write that as /8. Now /8 means, see, this is your 8, this is your 8, this is your 8, and this is your 8, right? These are the 4 octets. Value 8, which is 32. If I say /8, which means my first one is kind of locked in, and my next three are the host. So first one is the network, next three are host. So 255.0.0.0 can be written as /8. Similarly, /16 can be written for 255.255, because first two are for networks and we are locking them, and the second two are 0. So we will say 255.255.0.0 can be written like /16, because up till 16 we are going to make it the network ID. /24 means we are taking 8 plus 8 plus 8. 8 into 3 is 24. So we are saying that first three octets are going for network /24, and the last one is going for the host. So these are the cool ways of writing the subnet masking of class ABC /8 /16 or /24. Okay. Again, /8 means it's got 8 network and 24 hosts, like I said. /16 will be meaning 16 network and 16 hosts, like midway path, and /24 will be 24 network and 8 hosts. Now, how many hosts can we have in class A? You will see, when we want to calculate the number of hosts, we do a very simple mathematics there. We say, what is this octet value? H, this is 8, this H is 8, and this H is 8 as well, right? So 8 multiplied by 3, what is that value? 24, right? So we say 2 to the power 24. 2 to the power, the full value of the H octet, 8 into 3 is like 24. And this huge number will be the number of hosts, 16, or I will say close to 1 crore plus values for the number of hosts, or 1 crore, then 67 lakhs and 77,214, right? Similarly, for class B, the number of hosts will be, it's easy now. We know 8 plus 8 is 16. So 2 to the power 16, that is 65,536. And class C, it will be only the last one, which is 8. So 2 to the power 8 is 256. Now, if you look at the book of CCNA, they will say that it is actually 254. They will just minus 2. 2 to the power 8 minus 2, 16 minus 2, 24 minus 2. Why they do that? Because I said to you, the first one in the range cannot be used and the last one in the range cannot be used. That's for the network ID and the broadcast ID. So the book will say you the valid IP ranges 2 to the power 8 minus 2, which is 256 minus 2, 254 for class C. And it's absolutely correct. Here I've shown you the complete range, but yeah, the usable IPs between that, or the valid IPs between that, will be minus 2 for each of them. Now, looking at this in a very practical way, do we really want to use a class A IP with /8 in a network? Do we have got this amount of host? Never, right? It's such a huge number. So we want to break it down. So we will probably go for class C most of the time, 192.168, and we can break it down, and we can say that we need 250 plus people or 200 plus folks in one floor maybe, and we can make it one big subnet of 256 hosts there. But there is further to that I will come down slowly. But as of now, just looking into this particular slide, you will understand that most of the time we probably will use /24. Okay, now this /8, /16, and /24 are the default subnet mask breakup. We actually can break it up further, that I will show it to you in the further slides. All right, now let's quickly go to the further concepts. Now, this is one example which I really wanted to show. And that's about, let's say you have got 4 teams who are lining up in your company: sales, marketing, IT, and admin team, and all are going to have like 50 hosts inside, and you are being given the IP address 192.168.10.0/24 class C, and how you are going to assign the IP address range, or how you're going to break it in a nice way. So let's go through this and then check it out. What is the best optimum way to break it down? So let me quickly plug in my box there. Okay. Now, if I say 192.168.10.0, okay, and I will say /24. Now, /24, I have said to you that actually means that the subnet mask will be what? Will be 255.255.255.0. That is by default for the class C, right? Now, if I look into like this, then I will say there are 8 bits there. So 2 power 8, that will be 256 host can be done, right? For that particular range. Now, if I give that range, let's say for sales team, I give that range, for marketing also, for IT also, for admin as well. So let's say for sales only, I'll be giving 256, and what I need only 50. So 256 minus 50, I will be losing out close to 206 IP address. And if I calculate for all the 4 teams, if I go with the default values, then I will be losing close to 800 plus IP address, 206 into 4, right? So something that is not at all practical and realistic to go for that kind of solution. So what we are going to do is that, now here comes the method which I want to show you. Let me just draw one more. And this is called how to break the IP address or the subnet mask in the way which you want. Now we have broken down to /24, right? Now remember, 32 is the maximum, right? Now, as we move to the right hand side from 24 to 32, like I say /24, and I will go /25, I can go, or /26 I can go, and like that I can go, and so on till 32. As we move towards the 32, okay, your number of hosts will decrease. And as I move to the left hand side of 24, let's say /23, or probably /22 or /21, you will see that your number of hosts will increase. So let's have the values. /24, I said number of hosts will be 2 to the power 8 in that case, and that is actually because you are doing 32 minus 24, that comes to 8, right? Okay, and your 2 to the power 8 will be 256. What about /25? Your number of hosts will decrease, okay? And that is because it is 32 minus 25, which is actually 7. And here what you are getting, 2 to the power 7, that we know, 128, right? Similarly, let's say /26. That will be 32 minus 26, and that is actually 6. And here, if I make it 2 to the power 6, that is 64. Let's do one more, /27. That is 32 minus 27, and that will be 5. And 2 to the power 5 will be 32. So like this, you can customize and break as per your requirement. So the moment you see that your requirement is only 50 hosts, why do you want to go for /24? You can actually make it /26, which is the apt one. See, it is only 64, which means that yes, I can go with this number, because 128 looks too high, and 32 of course is quite less. 64 is a decent number, because if I have got 30, I mean 50 guys or 50 hosts, then 64 means let's see, now if I give like 64, then for sales team, let's say if I give 64, then your number will be 64 minus 50. So you are actually giving 14 more. And if you calculate that for all the teams, then 14 multiplied by 4, which is 56. You're only going to lose out 56 IPs compared to the initial 800 plus which you are going to lose. Now that's an amazing kind of gain, right? You're not good, and again the 14 will not be a loss at all. Suppose 2-3 more guys will be joining in like after 6 months. So you have got a buffer with you of 14 IP address which you can use it, right? So the most practical way of dividing this will be as per the host you need, and for that you do the slider, and the slider can be pushed from 24 to 26. Now let's see, if I want to break it down to 64, then how the range will look like. It will be like 192.168.10.0, and I will go here till 192.168.10.63, 0 to 63. That is one range. 64 you're getting. Similarly, next I can do 192.168.10.64. I will take now, and I will say 192.168.10.64 plus 64. That is actually 128. You're going to do 127 here, and that's the range keeps on. Again, you will say 192.168.10.128, and this time you will plug it to 64. So 192.168.10.191. Okay, and the last one will be 192.168.10.192, and you will take it to, let me just move this a little bit up. Okay, 192, and you will be taking it from 192 to just give me 1 second, there's a typo there. Yeah, now we can take it from 192 to 192.168.10. If I make it 64, 256, we will get 255. Okay, so now if I look, you will see, let me pull this up, and okay, now I will see this is our subnet 1, this is our subnet 2, this is our subnet 3, and this is our subnet 4. So these are the 4 subnets in a very intelligent way. Like what we have done, we have broken that into the number of hosts we actually need, not by the default class C, which is /24. In that we would have wasted a lot of IP address with no real use at all, and we break it down to the slider which we need /26, and we got nice and neat 4 subnets, subnet 1, 2, 3, 4, right? So overall, now how it will look like if you want to break it down into 4 departments with the proper subnet mask or the subnet range, it will be something like this: 0 to 63, 64 to 127, 128 to 191, and 192 to 255. Okay, I hope it's clear. Now that's just one of the examples I gave, okay, and how to break it down apart from the classic default slider. And in the real life, you will always be breaking it down not in the default slider mode, but as per, you will customize it as per your need of the number of the host which you need in the network, right? Or as per the head count in the site. If your head count is like, let's say 200 people, it makes sense to have a /24. If the head count is, let's say, just 50 people you're going to add, it makes no sense to make a 24. It will always make a sense to have a 26 kind of thing where you're getting 64. Okay, so that is one of the basic concepts of subnetting. Now how to sharpen this knowledge, because this knowledge is something which is elementary, which I gave you. Now you have to deep dive on this, and the only way to sharpen your knowledge in subnetting will be to practice, practice, and practice. Okay, let me just pull up some websites and show you if we can do that from a couple of sites. Yeah, we have got a lot of sites, actually tons and tons of sites, but the good ones I can show you right now. If you just go to Google and type in practice subnetting, there are a lot of them. I personally like this one, subnetting practice, which I used in my own time. This is something which gives you a pretty decent way, and you get a lot of like questions. You keep on doing them like every day, and you will be getting the answers as well. And there are others as well, okay, with all the graphics and all. They show you the diagrams, and you can practice them, and you can find out the range and the subnet mask which you need, and number of hosts and so on. Okay, so with that we conclude the topic of subnetting. Okay, and like I said, more practice will make you faster and better in this domain. Hope you liked the lesson. Thank you all for watching this. Cheers.